Hey friends. Okay, so next video that we're going to do in our diploma prep course, this would be video 9, and it is the back section of trigonometry. Okay, now just as a reminder, trig is usually the thing that 30-1 kids struggle with the most. It's probably the most in-depth thing that we do. And then of everything we do in trig equations and identities is probably the hardest of trig. Okay, so this is going to be a video. We're going to take our time. We're going to go through things nice and slow. You have the advantage with a video. You can shut me up at any time. You can back me up at any time. Or if you feel I'm speaking too slow, you can put me on chipmunk mode and I'll talk really, really fast for you. But let's take some time together and get you feeling really, really good about this. Okay, a reminder that trig is about, 27 to 33% in that range of your diploma. So it is a fair chunk. And so, we want to put our best foot forward and do what we can to make sure we have this down as well as possible. Okay. All right. So we're going to start with trigonometric equations. That'll be kind of the first half of this video. And then we'll switch into talking about verifying and proving identities. Okay, so trig equations. Trigonometric equations can be solved graphically or algebraically. To solve graphically, usually what we're going to do is put the left side into y1 and the right side into y2. Then the solution will be our x values of any point of intersection that you see. Fun thing with trig is you often have multiple solutions because these graphs, just like we talked about in the last video, these graphs are cyclic, right? So if I have a particular intersection here, I'm going to see it again a period away from there and a period away from there and a period away from there. Okay. Just remember as well, and this is for any sort of graphing conversation, your solution is the x value, not the coordinate point here. There was no y. We just kind of created a system using our graphing calculator. So your solution is only the x value of our point of intersection. Okay. Now, to solve algebraically, which is where we're going to spend more of our time today, we'll use our knowledge of the unit circle. Yay, that was a fun one. And by the way, that's in video 6. If you need a little refresher, if you're not doing these in order, video 6, I'll cover the unit circle for you, okay? And our skills in factoring, everybody's favorite F word. It's gonna be so fun. Okay, the general solution refers to all the values that are solutions. Just like we talked about in a few other instances, we talked about general solutions. We start with our first positive, and then we write the period of repetition after that, okay? If the domain is restricted, now different teachers are going to teach us different ways. Sometimes, especially when we get into negative domains, some teachers will tell you, hey, we're going to go, clockwise on the unit circle instead of counterclockwise on the unit circle. If you're cool with that, that's awesome. That's like the beautiful math way to do that. I don't tend to do it that way when I teach, just because I find it's actually confusing to kids. And my goal, especially with a diploma prep course, is not to confuse you. I want you watching these videos and feeling better than when you started. So what we're going to do is we're actually going to look at it from more the view of a window on a number line. And I'll show you that when we get there. Don't forget to talk about your restrictions. That is super, super important. It will not say on a question, hey, state your restrictions if they ask you to solve. It's understood that you're going to have to state your restrictions because you have to check your solution against your restrictions, okay? Okay, so graphically determine the solution to 5 cos theta plus 5 equals 3 cos theta plus 4 in the domain 0 to 360. Okay, so right away, let's just talk about a couple things here. You are going to want to, this is going to be your window setting, right? So that's your x min, that's your x max. And then the y values, well, I know that this is going to have a midline of 5 and then go up 5, down 5, so I have to get up to 10. This is going to have a midline of 4, up 3, down 3. So 10 is going to be my highest point. So maybe I want my y values to go right up to 10. Maybe I want to go a little higher than 10 just so that I don't have the maximum right at the edge of my screen. Sometimes it's a little easier to bring it down a bit. But essentially, you're just putting this into y1, this into y2. and then you're going to graph it, okay? The graphing picture that I show you here is from a Casio. A TI will give you the exact same picture, and you can see my window settings exactly as I've talked. So we have two different intersection points, one right here and one right here. So you're going to go and calculate those. If you're a Casio kid, it'll be GSolve intersect. If you're a TI kid, it'll be second trace 5, enter, enter, enter. For TI kids in particular, just make sure you're close to the one you want. You don't have to be right on it, but just somewhere close to it, and then it will calculate the thing it sees nearest. And then you'll have to do the process again over here. So you just have to move your cursor over here a little bit, and then go from there. Casio kids, when you go F5, F5, it'll go right to this one for you, and then you just have to right click and it'll jump over to the next one. Okay. Okay, so in the domain 0 to 360, I have two different answers. One is 120 degrees and one is 220 degrees. The question said theta, so I'm answering as theta. I'm in degrees. I'm making sure that my degree symbol is there as well. If you do not have your degree symbol there, your marker is going to think you're in radians, even though it says 120. If you don't have a degree symbol there, you're not in degrees. So that's super important. Don't forget your units. Okay. Okay, determine the general solution. Okay, so same question, but now the general solution. Now, if I go for a general solution, I kind of want to do it in as few sentences or statements as possible. So if I looked at this first guy, let's say my general solution is 120 plus. Let's say I can go right from there to there. Just for fun, humor me for a sec. Well, that'd be 120 to 240. So that would be 120n. Now, if that was the case, then I could go another 120. 240 plus 120 is 360, which is right here. And this is obviously not an intersection point. So I can't do that. Okay, that tells me right away I'm going to have to do this in two different statements. I'm going to have 120 degrees plus 360 because it's at 360 that I'll see it again. And 240 degrees plus 360. Okay. So my general solution would be written in two different things, 120 degrees plus 360 degrees n, where n is a member of the natural family. You can also say, I'm just going to talk about a couple things here, but let me finish saying my statement. Then 240 plus or minus 360 n, where n is a member of the integers. Now, I don't want you to get all boggled down, whether you wrote it this way or not. There's multiple ways you can write this answer, okay? You can also have a plus sign here without the plus minus. And then you can say n is a member of the integer family instead. Okay, your diploma often does this. And hey, if your teacher taught you Z for integers, that's awesome too. Your diploma doesn't tend to use Z, it uses I more than Z, but perfectly acceptable for you to write Z. Okay, so I guess the thing I need you to see here is if you're going to use the natural family, you do have to have a plus or minus there because you have to show you're going in either direction. If you use the integer family, you don't have to have a plus or minus there anymore because the integers will allow you to go negative. Okay. The other way sometimes we write this is like this with a bracket, and then we write the two statements inside here, which I actually often like better just to write it like this. So 120 plus 360 degrees n, and then 240 degrees plus 360 degrees n, where n is a member of the integers. Okay, so that's another way to do it, write the two statements, but they're combined with this open bracket to say theta equals both of these branches. If you do that, you don't close the bracket on the other side. This guy here is just meant to say, hey, I'm going to split into two different statements. Okay, awesome. Okay. Solve 4 cos x plus 2 equals 0 in the domain 0 to 2 pi. Now, take note that I can be 0, but I can't be 2 pi. That's something to just take into account. Okay, so I'm trying to get x by itself, which means, first of all, I need to get cos x by itself. So I'm going to subtract 2 and divide by 4. I think that'll probably feel okay for most of you to say I have to get cos x by itself. So if I subtract 2, that's going to give me 4 cos x equals negative 2. Then divide by 4, negative 2 over 4 would reduce to negative 1 over half. And now I'm going to say, okay, where does cos of x equal negative a half? Okay, now, things that we like to see in your work, we would love it if we started by saying, hey, first of all, the reference angle is cos to the -1 of a half. And so the reference angle here would be pi over 3. That's when cos is a half, okay? Then we can say, okay, cos is negative ratio, and I know that cos is negative in quadrant 2 and in quadrant 3. So my answers are going to look like that and like that, okay? Okay, and so then the first answer I get is going to be 180 degrees minus my, oh, sorry, I should be talking in radians right now, not in degrees. So my first guy will be pi minus pi over 3, my reference angle, and that'll be 2 pi over 3. And then my second guy will be pi plus pi over 3, and that'll be 4 pi over 3, right? Just remember that pi is 3 pi over 3. So it's essentially like 3 minus 1 and 3 plus 1, okay? All right, awesome. Then I double check that with my domain and I'm good to go, okay? So I showed my reference angle and then I showed my two answers. Great to draw a picture there too, just to show where those two angles. Okay, next, solve 2 sine x cos x equals sine x in the domain 0 to 2 pi. Now, very common that kids look at this and they say, oh, okay, I'm just going to divide everything by sine and then I don't have to worry about it. Fair point, but the problem is if you divide out the sine, you just lost half of your answers. Don't do that. You always want to look at these guys as a factoring question, which means I want to actually subtract sine from both sides. Remember, I can't factor, or I can, but it's useless if I don't start the factoring process where one side equals 0, okay? So I'm going to bring my sine x over here so that it subtracts sine x. And then I'm going to factor out a sine x. So if I factor out a sine x, I'll have sine x on the front, and then with a bracket, I'll be left with 2 cos x minus 1, okay? This is now the zero product principle. So what that means is each one of these could be 0. Either sine x is 0 or 2 cos x minus 1 is 0, okay? So if sine x is 0, I'm going to figure out where that happens. So sine x is 0 at 0 and pi. And then cos x equals 1/2 if we take that all the way, right? I just added 1 and subtract by 2. So then I'm looking at, okay, where's cos of x equal to a half? I'd be in quadrant 1 and quadrant 4. So that would be pi over 3 and 5 pi over 3. Okay, and then I put this all together. I want to make sure I'm taking into account that I'm in the right domain, and this was 0 to 2 pi. And I want to go in order from smallest to largest. I want to put this in set notation brackets. So it would look something like this: 0, pi over 3, pi, and 5 pi over 3. Okay, now, little tidbit, perhaps you looked at this question and you're like, hey, this is no fun. This is confusing. I don't like all these sine and cos x. They stress me out and make me want to assume the fetal position and rock back and forth and cry a little bit. By the way, nothing wrong with crying. Very therapeutic. It will release some stress hormones for you. It's okay to have a little cry. Great, but we also need a strategy if we're getting stressed out. So the other thing I can do here, let's call cos of x x, and let's call sine of x y. Now, you can do that as long as you say, let sine x equal y, and let cos x equal x. If you say that, your marker has to follow what you're doing, okay? If you don't say that, then your marker is going to be like, hey, what just happened? I don't understand. So don't do that. But you can do that and then say, okay, well, now this is 2yx equals y. And then say, okay, well, that'll be 2yx minus y equals 0 and factor the y out. Like that might feel less stressful to you if the sine and cosines are messing you up. The only thing you have to remember, if you do that, make sure you put it back at the end. The answer is not y equals 0. You have to remember that y was sine x. So sine x equals 0, and then you'll have to do that one extra step to figure out where sine x equals 0. Okay? Okay. Y'all with me? We're doing okay? We're not too stressed? Okay. Fractions, everybody's other favorite F word. Okay, solve sine x over 4 plus 1/12 equals sine x over 3. Now, anytime we have fractions in an equation, probably we just want to get rid of the fractions. If I multiply everything by 12 here, I won't have any fractions anymore. So to do that, it's sort of like I'm doing this. I'm going to say, okay, I'm going to multiply that term by 12. I'm going to multiply that term by 12, and then I'm going to multiply that term by 12. Okay, so then that's going to give me 12 over 4, which is 3 sine x. 1/12 times 12 is 1, and that'll give me 4 sine x, which is what I should have here once I figure out how to get my mouse back. There we go. Okay, so now I'm going to subtract 3 sine x from both sides, and I'll get 1 equals sine x. And then I'm just looking for, hey, where does 1 equal sine x, or where does sine x equal 1? Same sort of statement, right? Well, remember, Calgary Stampede, your sine is your y value. Where does your y value equal 1? That would be at pi over 2. Okay, so that would be the only answer for this one in that domain. Okay. All right. Now, again, this can look a little stressful because we got funky stuff happening inside the bracket. So if the funky stuff happening inside the bracket bothers you, ignore it. Call it A just for a sec, okay? Again, you need to say theta minus pi over 4 equal, or let theta minus pi over 4 equal A, okay? But then we're just looking at, okay, well, probably I want to subtract 3 and probably I want to divide by 2. Like those are kind of the straightforward starts. And that's going to give me 1/2. So we're looking for, where does cos of this thing equal 1/2? Well, we actually already answered that question on a previous slide. That would be at what? What did I say? Cos equals 1/2. So pi over 3 and 5 pi over 3, right? Quadrant 1 and quadrant 4. So then with this guy, there's just this extra layer of the fact that it's not an angle here, it's an angle minus pi over 4. So instead, we end up saying the angle minus pi over 4 could equal pi over 3, or it could equal 5 pi over 3. Now, if it equals pi over 3, to get theta all by itself, I'm going to have to add pi over 4 to both sides. And if I add pi over 4 to both sides, again, I'm just thinking about a common denominator, right? Let's make that over 12. So this would be 4 pi over 12. And then this would be, what, 3 pi over 12? So I get 7 pi over 12 when I add those together. Okay, and then the other guy would have been 5 pi over 3. When I add pi over 4 to that, oh, by the way, if I'm stressing you out because I'm doing fractions in my head, grab your calculator, friends. Just put 1/3 plus 1/4 in your calculator and you'll be good to go. Okay, don't be stressed. This is all good. Okay, so 5 pi over 3 as a fraction over 12 would be 15. And then adding the pi over 4 would be 3. So that sounds like, sorry, I said something wrong there. Let's do it together. My bad. Okay, so if I had that over 12, oh, that's why it's 20, because I multiplied that by 4. That was my mental math error. See, even math teachers make mistakes. Okay, so then that'd be 20 pi over 12, and then I'm going to add 3 pi over 12 to that, and that's where the 23 pi over 12 comes from. Okay, now, great conversation here. Make sure you double check your domain. Sometimes if you have to subtract a number, here we didn't, we had to add it, but you just want to make sure that you don't, the adding or the subtracting doesn't push your answer out of the allowable domain that you're allowed to answer. For instance, 2 pi would be 24 pi over 12. So I am very close to being pushed out of that domain, but I'm not, I'm safe. So these will be my two answers, but just something to watch for. Now, if that happens, probably all you need to do is get the coterminal angle to it, and that one will be within the domain, okay? So just little tidbits to think about. Okay. Solve cosecant theta equals negative 1.57 in the domain negative pi to 2 pi. Now, I've done a couple things to you here. One, I gave you cosecant, so I gave you a reciprocal one. The other is I have messed up with your domain a little bit. Now, forget about this, okay? This is the last thing you look at. We're just going to pretend we're going from 0 to 2 pi at all times and get all those answers first, okay? So if I do that, looking at cosecant, cosecant is the flipped version of sine. So instead of writing cosecant theta, I'm just going to change this to sine theta. I can do that as long as I flip the ratio, okay? Because we're dealing with cosecant as well, we want to talk about NPVs. I know that this is 1 over sine, and if it's 1 over sine theta, that means sine theta can't be 0. So where does sine theta equal 0? That would be at here and at here. And so those are pi away from each other. So I would say theta can't be 0 plus pi n, but I'm not going to say 0 plus anything, right? So I'll just say pi n, where n is a member of the integers. Okay. Fun fact, restrictions. This is what the restriction is, right? Otherwise known as my NPV. Restrictions always need to be written in general form, okay? You don't write your restrictions based on this domain. You always write restrictions in general form. Okay, so I got that. And now I'm going to write as sine of theta equals, so sorry, I skipped a step there in my PowerPoint, but I'm going to start this by sine of theta equals -1 over 1.57. Now, theta's reference angle will then be the inverse sine of 1 over 1.57, and that's what's giving me this. Okay, so you want to make sure you're in radian mode to do this. Couple of things I want to just reiterate with you. You probably already know them, but I don't know who you are, so I just want to make sure everybody's cool. So when I go to get the reference angle, I'm always inversing or inverse signing or arc signing the positive version. I never handle this negative when I'm going to figure out the reference angle. Okay, always do the positive, and then you'll always get the reference angle. Once I've established what my reference angle is, take note, I did not round to the nearest tenth of a radian right now because that is not a final answer. I don't want to run into a rounding error by rounding too soon. So that's why I have 4 decimal places there. Now I'm going to think, okay, well, where is my sine ratios negative? And I know that's in quadrant 3 and in quadrant 4. So I want to apply this reference angle right here into quadrant 3 and 4. Okay, so for quadrant 3, I'm going to go pi plus the reference angle. And then for quadrant 4, I'm going to go 2 pi minus the reference angle. And those are final answers, so I am rounding to the nearest tenth. Now, here's what I was talking about earlier around, hey, think about it as a window, okay? So essentially, I want you to think about it like this. I asked you to just start from 0 to 2 pi. And so far, we've gotten two answers, 3.8 and 5.6, okay? What this is telling me, this window here, is actually that I'm allowed to now have a window that looks more like this, okay? Where I'm going to go to negative pi as well. So to see if I can fit anything else in that window, I get coterminal angles. So to get coterminal angles, I'm just going to subtract 2 pi. Okay, so if I take 5.6, I'm just grabbing my calculator. I'm going to do it with you. If I take 5.6 and subtract 2 pi, I get 0.8. Oh, sorry, I divided by 2 pi. Subtract 2 pi. I get negative 0.68. Negative 0.68 is now within that window. Okay, that was 5.6. And then if I take 3.8 and subtract 2 pi, I get negative 2.4. Now remember, pi is negative 3.14. So I just said negative 2.48. So that is totally okay. Negative 2.48 is also within that window. So I'm going to actually have 4 different answers here, given the domain that has been specified to me. Okay. So when rounded, I get negative 2.5, negative 0.7, 7.3, sorry, 3.8, and 5.6. I got to read my own PowerPoint properly. Let's try that again. Negative 2.5, negative 0.7, 3.8, and 5.6. Okay, cool. Okay, next up, solve sine squared theta minus 2 sine theta minus 3 equals 0. And we're going to do this in degrees. We're going to be from 0 to 360 degrees. Now, what I want you to see here is a friendly quadratic. Okay, you've got a sine squared with a sine and then a number with no sign. Okay, that speaks of an x squared with an x and a number with no x. Okay, again, if you want to do a substitution first, if you want to say, hey, we're going to let sine theta equal x, and then write this as x squared minus 2x minus 3, beautiful. Okay, nobody will yell at you about that. Everybody will be happy. If you don't want to, if you want to work with what's given to you, totally fine as well. Okay, but either way, if you're going to make that substitution, make sure you say what you're doing. Okay, as markers, we can't read into what's not been given to us. So just be careful with that. Okay, so I am going to show you an example of a substitution. I'm not going to do a lot of the substitution ones, but just to show you, hopefully to keep your stress level down a little bit, let's go through one. So if I said let a equal sine theta, now I'm looking at a squared minus 2a minus 3 equals 0. Hey, friends, can I get on a soapbox for a sec? Really important that you say equals 0. Okay, if you drop that equals 0, nothing that you say in math makes any sense anymore. Okay, you can't use the zero product principle if your product doesn't equal 0. Okay, so it is super, super important in your communication of this stuff that you keep that equals 0 there. Okay, so now we're factoring. So a minus 3 times a plus 1. And then we've got the zero product principle because that equals 0. So a equals 3 and a equals negative 1. Now, remember, a is not a is sine of theta. So I got to put it back now and actually solve for where sine of theta equals negative 1 and where sine of theta equals 3. Sine of theta equals negative 1 at 270 degrees. And then sine of theta equals 3 doesn't happen. Okay. If you try to inverse sine of 3, you'd get some sort of an error, a math error, or a domain error. But what I want you to remember, if you think about your sine graph, the range of that sine graph is from negative 1 to 1. Sine ratios can't be beyond the range of negative 1 to 1. So for that guy, you just say no solutions. Okay. Then I go and check my domain. My domain is just a straightforward 0 to 360. And so my answer is 270. Now, if I had wanted to check this as far as using my graphing calculator, what I really want to talk about here is that guy. When you put that in your calculator, it has to look like this. Okay, meaning the square actually goes after the sine x. Now, if you're a TI kid, when you press the sine button, it automatically opens up a bracket like that. So you'll want your x and then close that bracket, but then there also needs to be a bracket around that. Okay, so sine x in and of itself has to be entirely inside a bracket before you put the square in. Okay, awesome. Okay, determine a trigonometric, oh, I like this question. Determine a trigonometric equation that has solutions of theta equals 225, 270, and 315. Okay, well, here's how I'm going to tackle this. I've got 270. Well, 270 is this guy right here, right? And then 225 would be this guy, and 315 would be this guy. So I am trying to connect these three solutions together. Okay. Okay. Well, I'm actually going to take a look at these guys together first, because I know that those are a 45-degree reference angle. And I'm thinking, okay, how could I connect quadrant 3 and 4 together, that could be with sine, because sine is both negative in quadrants 3 and 4. Okay, and so the ratio there would be root 2 over 2, or if it was unrationalized, 1 over root 2. So I'm going to say, hey, sine of theta equals negative root 2 over 2. That would give me those two solutions. Okay. So I'll come back to that guy in a second. Let's just look at this guy now. If I just want that solution, well, I could say cos of theta equals 0, but the problem with cos of theta equals 0 is I would get this one as well. I don't want that one. So actually, I'm going to have to say sine of theta equals -1. That's the only solution for sine of theta equals -1. Okay. Now, I have to take this and create a trigonometric equation with it. Well, that means I'm going to want to have some factors. So this guy's an easy factor. This will be sine of theta -1 equals 0. So that'll be one factor. If I go back down to the other guy, I'm just going to switch back to green here. This would be 2 sine theta equals negative root 2. So then I've got 2 sine theta plus root 2 equals 0. Or if you were unrationalized, it'd be root 2 sine theta plus 1. Okay, that's okay too. Then I just put both of those together side by side and set it equal to 0, and there's my quadratic. Okay. That's fun. Okay, I'll put the typed version of what I just said. Up, and there we go. Yay for us. We can do this. Okay. Using the graph below, the first positive solution that satisfies f of x equals g of x to the nearest hundredth. Okay, we can do that. First positive solutions right there. So I'm trying to figure out what that guy is. That was a really bad line, sorry. It's 1, 2, 3, 4 tick marks to 2 pi, sorry. So that means everything here is half pi. Okay, so then it said rounded to the nearest hundredth. So I'm just going to go pi divided by 2 in my calculator, figure out what that decimal is, and properly round that decimal to the nearest hundredth. And that would be 1.57. Okay, 1.57. Okay, now let's get into some identities. An identity is a mathematical statement that simply means the left side and the right side are the same thing. Complicated trigonometric expressions can be simplified using our knowledge of identities. This is where your formula sheet is going to be used a lot. So if you don't have a formula sheet handy, grab one. You can, if you don't have one from the teacher that you've been working with, just go Google Alberta Ed 30-1 formula sheet and you'll get it. Okay. We are going to go through two different sort of conversations here. One is on how to verify an identity. If we want to verify an identity, we substitute a value in for theta and show that the right side equals the left side. If we want to prove an identity, we need to make the left side and the right side say the same thing as individuals. Okay, this means we can't do something to both sides of the equation like we would if we were solving. So really important on a verification and on a proof, I would always start by just drawing a line down the middle. So you got something equals something. Okay, you're going to draw a line right down the middle because you don't want to actually put equal signs here because that's what you're trying to prove. Okay, then what you'll do is you'll work on this side all by itself. So you'll go equals, 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 and then you'll go over to here and you go, oh, okay, I can do that and I can do that. Oh, look, these guys now say the same thing. And so I conclude left side equals right side. Okay, that's what a verification or a proof should look like. Okay, you're working on the left side separately. You're working on the right side separately. I know there are teachers out there that say you can't work on both sides. You have to pick one side and make it turn into the other side. You don't have to do that for your diploma. You're allowed to work on both sides. You just can never cross sides, okay? So if I went and said, oh, I'm going to bring this term over here, the second I cross that green line that I've drawn there, your proof or your verification is invalid. Okay, so don't do that. This is also important. You must conclude at the end that the left side equals the right side. Okay, ideally, I would love it if you actually wrote out the words left side equals right side. Okay, this is the one case in 30-1 where they will accept an abbreviated version of LS equals RS. If you've been taught QED, that's also acceptable. Or if you've been taught Tombstone, that's also acceptable. Okay. Don't actually write RIP in your Tombstone. Okay. Some hints. Now, I want to say right off the bat, when I say hints, that's all they are. They're hints. I'm not saying you do this all the time. You essentially, with any proof, you just do something that you can see. Okay. And then as you just keep doing things you can see, you hope, and usually it will, that it works itself out. Usually you want to start with the more complicated side. If you see squares on your trig identities and numbers, especially the number 1, like, think about Pythagorean identities. Pythagorean identities, if they can be used, are often much quicker than something like converting everything to sine and cosine. But in that same breath, sometimes you want to change everything to sine and cosine. Always simplify complex fractions, so combine fractions together or sum or difference of fractions. So get everything as a common denominator, get everything as one fraction. Watch for factoring. And then sometimes it's helpful to multiply the numerator and the denominator together by the same function, just like something like the conjugate. Okay. Okay. Simplify tan A times cotangent A plus sine A times cosecant A. State the non-permissible values for the variables given. Okay. Pardon me. So first of all, if tan A, if I'm just thinking about non-permissible values right now, tan is sine over cos. So if I see tan, I know that cos of A can't be 0. If I see cotangent, I know that sine of A can't be 0. Then over yonder, I've got cosecant of A, but that sine of A can't be 0 again. So cos of A can't be 0 and sine of A can't be 0, which is every quadrantal angle. Okay. And so that would be pi over 2n, where n is a member of the integers. Okay, so the first thing I did there was just I wrote it all as sine and cos, just so I could see what's on the bottom of fractions. So NPVs, I've already said that. A can't be pi over 2n, where n is a member of the integers. Again, restrictions, NPVs, I don't care what you call them, they have to be written in general form. Okay. Okay, now this is easy peasy. This guy's going to end up being 1, right? Because sine divided by sine is 1, cos divided by cos is 1. Sine divided by sine is 1. So I end up with 1 plus 1. So that simplifies to 2. Okay. Easy. We got this. We're going to make 100 on this diploma. Okay, simplify cosecant B over tan B plus cotangent B. State the non-permissible values. Okay, so tan B is sine B over cos B, and cotangent B is cos B over sine B. But what I want you to notice, first of all, is as I do that, I also changed the orientation. I'm going to write this as a left to right division statement instead of a complex fraction, which would be a fraction in either the numerator or the denominator. Okay, now I see sine on the bottom, I see cosine on the bottom. I'm going to have the same non-permissible values that I just did. Theta or b this time can't be pi over 2n. Now, I can't change this to multiplication and flip the next fraction if there's multiple fractions going on here. So the first thing I have to do is add these together. I need a common denominator to do that. My common denominator is going to be sine b cos b. So for this guy, I'm going to need to multiply him by sine b over sine b. And for this guy, I'm going to need to multiply him by cos b over cos b. So that's going to end up being sine squared b plus cos squared b over sine b cos b. Now, some of you are following along here and you're like super excited and you're like, dude, sine squared b plus squared b is 1. And dude, you're right. Don't do it yet, okay? The general rule of thumb is if you do two things at the same time to the same item, you're not showing enough communication. Okay, so I can't change this to 1 right away because right now the communication that I'm doing is that, hey, I'm getting a common denominator and this is what my common denominator is going to look like. Okay, the whole, hey, sine squared plus cos squared equals 1, that's going to have to happen in the next line. Okay, so just watch that you don't get, because I know these are exciting, watch that you don't get so excited that you end up doing two things at once. Okay. Okay, so I'm going to change this to multiplication. I'm going to flip it, and I'm going to change this to 1. Now, you may look at me and say, dude, you just said I couldn't do all of that. Everything I described, changing it to multiplication, flipping it, and writing sine squared b plus cos squared b as 1, none of them affect each other. Okay, so it's like I'm just handling all three items at the same time. I'm not doing two things to one item. Now, even in my slide, I didn't do that. First of all, I just changed my sine squared to, or sine squared plus cos squared to be 1. Now I'm going to flip it. Okay, so when I flip it, I end up with sine b over, or sine b times cos b, all over sine b. And then my sine b's will divide out, and I'm left with cos b. Okay? Yay! All right. The simplified form of sine b plus cos b all squared minus 2 sine b cos b. Well, this is a binomial squared. If I go to square that, I square the first, so that'd be sine squared b. Double the product, that would be 2 sine b cos b. Square the last, so that'd be cos squared b. And then I've got this minus 2 sine b cos b. Hey, if I just stressed you out by saying something that you're not familiar with, I said square the first, double the product, square the last. If that's not something you've been taught, don't worry. You're still going to do great on this diploma. You just have to think about it like this. Sine b plus cos b squared is sine b plus cos b times sine b plus cos b. And then you just have to FOIL it out. Okay? Okay, this guy and this guy give me 0. And then this guy and this guy give me 1. So the answer is going to have to be B. Okay, I'm just going to clear that and good. Okay, the expression cos 85 cos 30 plus sine 85 sine 30 can also be written as this. A question like this looks intimidating at first because you're like, what the heck? I don't know what cos of 85 is. I don't know what cos of 30 is. You're right. You don't. That's okay. Step back for a sec. I want you to think about this as, hey, this is like an A and a B. This is cos A cos B plus sine A sine B. That's the same as saying cos of A minus B. So 85 minus 30, I'm looking at the cos of 55. Okay, now if this was a legit multiple choice question on your diploma, you could just type this in, take a look at what the decimal is, and compare these 4 decimals as well. Okay. All right. The expression cos x minus y minus cos x plus y can be simplified to what? Okay, so I've got essentially like a cos of a minus b here, and I've got a cos of a plus b here. So I'm just going to go to my formula sheet. These are things on a formula sheet. I'm going to say, okay, cos of a minus b is cos of a cos of b plus sine of a sine of b. Okay, then I'm going to minus, don't forget, when you minus, you then have to open up a bracket because if there's multiple terms in here, the negative sign will apply to each term inside the bracket. Okay, so then this would be cos of A cos of B minus sine of A sine of B. I find it incredibly hard to say B and write Y at the same time. Okay, now what am I looking at? I'm looking at cos of x, cos of y, minus cos of x, cos of y. That'll be 0. And then sine of x, sine of y, minus negative sine x, sine of y. That'll be 2 sine x, sine y. So my answer will be D, 2 sine x, sine y. Okay. Yay. Okay. Determine all the values of x where the expression sine x over 1 minus tan squared x is undefined. Okay, so couple of things. First of all, why are things undefined in the first place? I can't have 0 on the bottom of a fraction. So if I just pick on this guy for a sec, 1 minus tan squared x can't give me 0. Well, that means 1 can't equal tan squared x, which means tan x can't equal plus or minus 1 when I square both sides of that. Well, when does that happen? That happens at all my pi over 4s, essentially. Okay, which would be pi over 4 plus pi over 2n. So this guy is in play. This guy is no longer in play. This guy has that statement, pi over 4 plus pi. This guy does not have that statement. Okay, so that was kind of a 50-50 card. We're going to look at either A or C now. Okay, now where would another NPV come from? If one exists, well, actually, friends, one does exist because I have tan. Anytime I have tan, I need to think about the fact that that's sine of x over cos of x. So cos of x can't be 0. Where is cos of x 0? Here and here, which would be pi over 2 plus pi n. So C is the winner, winner chicken dinner. That would be my total non-permissible values there. Okay. Okay. An expression that is equivalent to cos of 2x plus 2 sine squared x all over 1 plus tan squared x. Okay. Well, I can see that this is going to involve some identities, and I'm just going to try and start playing with things. So grab your formula sheet because that's something that you're going to want to work with. Cos of 2x. If you go down and look at cos of 2x, you have 3 different possibilities there. You will notice you have cos squared minus sine squared. You have 2 cos squared minus 1. And you have 1 minus 2 sine squared. Well, personally, I want to pick the 1 minus 2 sine squared because I see a plus 2 sine squared of x here, and that's just going to leave me with a 1 on top. That's probably going to be kind of fun. Okay, so I switched that to be 1 minus 2 sine squared x. Then I also on my formula sheet noticed that 1 plus tan squared x, that is a direct one on your formula sheet. It's secant squared, so I just changed that to secant squared. Now, my minus 2 sine squared x plus 2 sine squared x is going to be nothing. So I'm left with 1 over secant, 1 over secant squared. Well, if secant squared is the flipped version of cosine squared, then the flipped version of secant squared would be cosine squared. So that'll be A. All right. Prove it. Now, when we prove, we're going to do the line and we're going to have our left side equals right side. Okay. I can do whatever I want on the left side. I can do whatever I want on the right side. And then go from there. So on the left side, I probably want a common denominator there. So my common denominator is going to be 1 plus sine x times 1 minus sine x. Okay, 1 plus sine x times 1 minus sine x. So I needed the 1 minus sine squared, or sorry, sine x on the top. of the first guy, and then I needed the 1 plus sine x on the top of the second guy. Now, if I clean this up, negative sine x plus sine x is gone. It adds to 0, and then 1 plus 1 is 2. On the bottom, those are actually conjugates being multiplied together. So if you understand that that's going to give you a difference of squares, you can go right to 1 minus sine squared x. If you're not sure of that, you can just multiply first outside, inside, last. You will still get to 1 minus sine squared x. Okay, now at this point, I could say, hey, 1 minus sine squared x is cos squared x. Again, I'm just using my Pythagorean identities on my formula sheet. If sine squared theta plus cos squared theta equals 1, then I could bring that sine squared theta over and say cos squared theta equals 1 minus sine squared theta. Okay, that is allowable to do. You're allowed to manipulate the formulas that you have on your formula sheet. So I could either switch this to cos squared, or I could take this and switch that to 1 minus sine squared. It doesn't really matter what I do, as long as I get to a point where both of them say the exact same thing. Okay, so I decided I was going to change my 1 minus sine squared x to be cos squared x. And then I concluded left side equals the right side. Okay. Okay, verify. Now, super important with a verification that you plug in the value you were given right away. Okay. Now, this might be a bad example to say that with, because you're looking at this and saying, well, what else would I do? But let's say, I don't know, let's say here, I'm going to sidebar this for a second. Let's say you were given 2 tan of b over 1 minus tan squared b, and you were asked to plug in pi over 3. Okay, what I would want to see there is 2 tan of pi over 3 over 1 minus tan squared of pi over 3. And then you're going to figure what tan of pi over 3 is, and you're going to work with the numbers only after that. Okay. Don't look at this and say, oh my dear, that equals tan of 2 theta. Now, yes, that is a true statement, okay? But you do not, in a verification, you do not switch identities. You don't do any identity work in a verification. You have to plug in the value directly into the angle and then work with the ratios and the numbers only. Okay, so no doing identity work like that on a verification. Okay, which is why I said this one was sort of a bad example to have that conversation with, because there really isn't identity work that you could do here. Okay, so here I go. I am going to throw my line down so I can work with the left side and the right side separately. And everywhere I see a, that should actually say a equals pi over 6, not theta. My bad. Anytime I see the angle, though, I'm going to replace it with pi over 6. So that'll look like this on that side. And then on the other side, you'll just say sine of pi over 6 plus cos of pi over 6. I got to figure out what sine of pi over 6 is. I can use my unit circle to help me. That's going to be 1/2. Cos of pi over 6 is root 3 over 2. So every time I see sine of pi over 6, I'm replacing that with 1/2. Every time I see cos of pi over 6, I'm replacing that with root 3 over 2. And now I'm going to work on the math. So 2 times 1/2 is just 1. So this will end up being 1 plus root 3 over 2. I'm going to change my 1 to be 2 over 2, so I get a common denominator there. So that'll be 2 plus root 3 all over 2 on the top. On the bottom, I have 1 plus root 3 all over 2. And then over yonder, I've got that 1/2 plus root 3 over 2. So that'll also be 1 plus root 3 over 2. Okay, so I've done what I just said I would do, 2 plus root 3 over 2 and 1 plus root 3 over 2. But I wrote it as a left to right division statement, again, just so I didn't have those complex fractions happen. If you have a common denominator, For fractions, you can just divide the numerators, or if you don't like that, you can multiply by the reciprocal, whatever you like best. Okay, so over here, I just got that as a common denominator. So I end up with 2 plus root 3 divided by 1 plus root 3. Now, these guys don't quite look the same yet. Okay, and this often happens where things look not quite as we want them to. And so one strategy that we often try when we're doing that is we're going to take one of them and multiply by the conjugate. So I'm going to take this guy and multiply it by 1 minus root 3 and just see if that's helpful. Okay. On the top, I have to FOIL this out. So I'm going to end up with 2 and then minus 2 root 3 and then root 3 plus root 3 and then minus 3. And then on the bottom, I'll end up with 1 minus root 3. Sorry, 1 minus 3 because it's root 3 times root 3. Okay, so I took my my negative 2 root 3 and my positive root 3 and combined them right away to get that negative root 3. Okay, so then 2 minus 3 is negative 1. And then down here, I got negative 2. And so then I'm going to factor out the negative from the top and the bottom. And that's going to give me negative 1 over negative 1, which would just be positive 1. So that equals 1 plus root 3 all over 2. Now they say the same thing, and I can conclude left side equals right side. Okay. Again, I want to make sure you don't feel I'm skipping anything. I want to make sure I'm explaining myself well. This guy here, I said this could be like negative 1 plus root 3 over negative 2, and then my negative divided by my negative would create that positive there. Okay. All right. Cool. Now, let's prove it. I like this proof because it kind of flies in the face of the hints I just gave you. Remember that hints are just that. They're hints. They're things you could try. Okay. One of the hints I gave you was, hey, start with a more complicated side and see if you can make it more simple. Problem is, this guy is the more complicated side, and I don't know anything to do to make that look simpler. Okay, so I'm not going to do that. I'm going to actually start with the simple side and see if I can make it more complicated. I know that this is over 1 right now, right? Anything is understood to be over 1. But I know that I want this as my denominator. So let's just multiply this by sine A plus cos A over sine A plus cos A. Okay? That's how I'm going to try and figure this guy out. Okay, so here we go. And that's what I've done. So on the top, I'm going to FOIL that out. I'm going to have sine A times sine A, which will be sine squared A, and then sine A cos A again, and then cos squared A. On the bottom, I'll have sine A plus cos A. Now I can see that sine squared A plus cos squared A gives me 1. And then, hey, look at that. The left side equals the right side, and I am super stoked. Okay, so it actually wasn't as bad as maybe you thought it would be. Okay, awesome. The exact value of tan of 75 can be written in the form a plus root b. Determine the values of a plus b. So there's a couple things that I want to kind of tweak in your head when you read a question like this. First of all, it said exact value. I know I've said this in several of the other videos, but essentially, if you're not giving rounding instructions, you must answer an exact value. So this question is actually being even kind to you. But exact value of a trigonometric ratio kind of says to you, hey, we're going to use our unit circle for this, right? Or we're going to use special triangles or however you like to do that. Then you look at the number 75 and you're like, that's not on my unit circle in the nice, pretty ones of the unit circle. So what to do? Okay, well, is there two numbers that I can add or subtract together that are on my unit circle, that are friendly ones that we've talked about, that would add or subtract to 75? And the answer to that is yes, 30 and 45 will do that. So I'm going to say, hey, tan of 75 degrees is the same as saying tan of 45 degrees plus the tan or plus 30 degrees, okay? That is a trigonometric identity. You're going to get the formula sheet out. And that's tan of A plus B. So tan of A plus B is tan of A plus tan of B all over 1 minus tan A tan B, okay? Or this. Sometimes it's helpful too, friends. When I just rhyme that off, put a little A and B there so that when you go to write it on your formula sheet, you're not going to mess up what's what, okay? Okay, tan of 45 is root 2 over 2, and tan of 30 is 1 over, sorry, did I just say tan of 45 is root 2 over 2? My bad, sine of 45 is root 2 over 2. I should pay more attention. Tan of 45 is 1, and tan of 30 is 1 over root 3. Now, whether you say 1 over root 3 here, or you say root 3 over 3, totally fine either way. Okay, so I plugged in my 45s and my 30s. I now need a common denominator up on the top here. So I'm going to call this 1 root 3 over root 3. And then same thing down here. Actually, this is going to be 1 minus 1 over root 3. So I'm going to call this 1 root 3 over root 3. And then I'm going to write it as a left to right division statement so that I don't have to deal with those complex fractions. So this is the top, root 3 plus 1 over root 3. This is the bottom here, root 3 minus 1 over root 3. And then I can multiply by the reciprocal, or I can see that I have common denominators and just divide the numerators. No matter how you look at that, you're going to get root 3 plus 1 over root 3 minus 1. Now, that's a great answer. It's just not in the form a plus root b. I don't know. Maybe my head is cutting that off. I'm going to just hide my head for 1 second so you can see what I'm saying here. The form I need to answer in looks like that, a plus root b. Okay. Sometimes when I'm recording these things, my head moves. I can move my head around, so sometimes I forget where exactly my head will show up. So just in case I was cutting that off, there you go. Okay, so if I want to deal with this, then I'm going to multiply by the conjugate. Essentially, I'm going to rationalize the denominator is what I'm going to do. So I'm going to multiply this by root 3 plus 1, and then same thing on the top. Okay. If I do that, I end up with 3 plus root 3 plus root 3 plus 1. And then on the bottom, I end up with 3 minus 1. Okay, so that gives me 4 plus 2 root 3 over 2. And then everything is divisible by 2. So that'll give me 2 plus root 3. Now that's awesome because that's exactly in that form. So now I can say, hey, A equals 2 and B equals 3. Okay. Right. If I wanted to check this, I could just grab my calculator and go tan of 75 and see the random decimal that my calculator gives me, and then take my calculator and type 2 plus root 3, and I'd be looking at the same random decimal, which means maybe that decimal isn't all that random. Okay. Awesome job, guys. Okay, if sine of theta equals 5 over 13 and cos of beta equals negative 4 over 5, and both angles are in the same quadrant, determine the exact value of sine of A, alpha minus beta. But when I see alpha minus beta, I just know that's A minus B. That's right on my formula sheet. It actually is alpha minus beta on a formula sheet. But I know that sine of A minus B is sine of A cos of B minus cos of A sine of B. Okay, so there I go. Do I know the sine of alpha? Yes, I do. It's 5 over 13. So I'm going to replace this guy here with 5 over 13. I know the cos of beta. I'm going to replace that with negative 4 over 5. But here's the problem. I don't know cos of alpha or sine of beta. So to do that, I'm going to have to do a little bit of discovery, a little bit of detective work here. I know that both angles are in the same quadrant. So if sine is positive and cos is negative, that's going to happen in quadrant 2. So I'm going to actually draw out quadrant 2. And I know that my sine of alpha is 5/13. So that would be my opposite over my hypotenuse. And then I can Pythag my way to the base of this, which would be -12. I do need to call that 12 because, or -12, sorry, because I'm the x values on that side of the y-axis are negative. Likewise, over here, I knew that cos of beta was -4/5, so that's adjacent over hypotenuse. And then I Pythag my way to the height for that guy, and the height of that guy is 3. So now I know my other two pieces. I know that cos of alpha will be -12/13. And I know that sine of beta will be 3/5. So I plug in all of those ratios. And I'm just going to do the math. So this is -20/65, and this is -36/65. And so I end up with -20 plus 36, which would be 16. So the solution to that will be 16/65. Okay. All right. Yay. Algebraically solve the following in the specified domain. So now we're back to equations, but this time we involve some identities. So I see here cos of 2 theta. I don't want to ever work with cos of 2 theta. I don't want to work with a double angle. So right away, I want to swap that out. I have 3 options to swap cos of 2 theta out with. But I don't want to use an option that involves sine because I'm not going to be able to try and factor this out if there's both sine and cos going on at the same time. So that leaves me with the 2 cos squared theta minus 1. I want to switch this to be 2 cos squared theta minus 1. Okay, so that's going to give me 2 cos squared theta minus 1 plus cos. I'm just going to bring that -1 to the other side so it looks more like that friendly quadratic that I've come to know and love. I'm looking for 2 numbers then to multiply together to give me -2, the outside numbers multiplied together, and add together to give me 1. Nobody cares how you factor, whether you do decomposition, cross product method, inspection, whatever floats your boat. Just make sure you can get to the right factors, okay? I'm showing you right now decomposition, but you don't have to do that, okay? As long as you can get down to this line somehow and you've got it correct, we are very, very happy. Now, I'm at the zero product principle. 2 cos theta minus 1 equals 0, which means cos theta equals a half, or cos theta equals -1. Where does cos theta equal a half? That'd be pi/3 and 5 pi/3. Remember, I'm ignoring my domain at the moment. Where does cos of theta equal -1? That would be at pi. Now I want to take into account my domain. Okay, be careful. Lots of kids look at that domain and then they'll be like, oh, okay, well, this is outside my domain, so I'm just going to scratch it off. The problem with that is you need him to get the coterminal angle that should be part of your answer. Okay, if you just cross him off, you're actually going to miss the coterminal opportunity. Okay, that's why I want you to do all this stuff from 0 to 2 pi first. Okay, so I'm going to subtract 2 pi. If I subtract 2 pi from pi/3, that's going to give me -5 pi/3, which is actually outside of my domain. But if I take 5 pi/3 and subtract 2 pi, that'll give me -pi/3, and that is within my domain. If I take pi and subtract 2 pi, I get -pi, which could be in my domain, except that there's no equal sign here. So I can't be -pi. Okay, so my final answer, if you had followed that conversation, would be -pi/3, pi/3, and pi. -pi/3, pi/3, and pi. Okay, and again, don't want you to feel I'm skipping anything. To test out the other guys, I just kept subtracting 2 pi from each one of these guys, was the conversation I was doing there. Okay. If this had said, hey, let's go to, I don't know, 7 pi, well, then I would just keep taking these guys and I'd keep adding 2 pi to those guys until I go beyond the window. Okay. Awesome. All right. Algebraically solve the following. Okay. So let's talk non-permissible values first. Secant is 1 over cos, so cos can't be 0. Cosecant is 1 over sine, so sine can't be 0. And this is a good time for me to have a quick little conversation with you about us math teachers and how sometimes we're lazy. Do you notice that I just said secant is 1 over cos? You got to be really careful in your communication. You got to be really careful how you write this stuff out. You can't write cos all by itself. You can't say 1 over cos. You can't say secant. It's secant of theta or 1 over cos of theta, okay? Make sure you have an angle represented then. Even though lazy teachers like me don't say theta, I should, okay? Okay, so non-permissible values then will be if sine of theta can't be 0 and cos of theta can't be 0, that would be essentially 90 degrees n, where n is a member of the integers. Okay. So 90 degrees n, where n is a member of the integers. Now, I've switched everything to sine and cosine. And now if I'm dividing 1 over cos squared divided by 1 over sine squared, that's going to be sine squared over cos squared, or sine squared theta over cos squared theta. And then I want to multiply everything by sine squared theta cos squared theta so that I get rid of my fractions. Okay, so essentially, I'm going to take this guy, multiply it by sine squared theta cos squared theta. Same thing on this guy and same thing on this guy. Remember, this is now sine squared over cos squared. So if I multiply this guy by sine squared theta cos squared theta, my cos squared theta is divide out and I'll just be left with sine squared theta. If I multiply this guy by sine squared theta cos squared theta, my sine squares cancel out and I will be left with cos squared. And then here, my cos squares will cancel out and I'll be left with sine squared times the sine squared. So that'll equal sine to the 4. Okay. All right, I'm going to clear that and just catch up with the typing of it. There we go. Okay, now, in order to try and factor this, I would like everything to either say sine or cos. So probably it makes most sense to take my cos squared theta and switch it to 1 minus sine squared theta. Okay, so if I do that, that would leave me with this. Remember, whenever you do that substitution, make sure it's in the set of brackets because the negative sign that you see here has to apply to both of those guys. Okay, so that'll be a -1 and then a plus sine squared. So that'll be 2 sine squared theta minus 1. I'm going to bring everything over to one side so that I can factor it. So this is my leading, or this is my highest degree here. So I would like that leading coefficient to stay positive. So I'm going to bring everything else to the other side. And so I'd be looking at sine to the 4 theta minus 2 sine squared theta plus 1. Now I'm ready to try and factor that. Looking for two numbers that multiply together to give me 1 and add together to give me -2. So that would be -1 and -1. And so I'm left with a statement that says sine squared theta minus 1 equals 0, which is sine squared theta equals 1. Square root both sides, sine theta equals plus or minus 1. So where does sine of theta equal plus or minus 1? Well, at 90 and at 270, the problem with that is, oh, it's my NPVs. So actually, there is no solution to this particular question. Okay. Now, before you yell at me, maybe you're throwing stuff at your computer screen at the moment because I just made you do all that work to get a no solution. Hey, as an aside, you throwing things at your computer is only hindering you, not me. But just remember, it's just as powerful to be able to do the math and say that it doesn't work. That is just as powerful as doing the math and getting an answer, okay? So don't let that frustrate you. It's totally okay that you ended up with a no solution and you have the proof to back it all up, okay? It's all about the communication. It's not necessarily about the answer, okay? All right, my friends, that finishes this one. And that finishes trig, okay? So in the next video, we will tackle log or exponents and logs, okay? But again, I know I said this at the beginning of this video, but trig is often the hardest thing. So, you know, if you need to watch this video a couple times, great. You know, if you have a question and you want to send it to me, just you need some clarification, that's great too. Just know that you got this, okay? Know that you can do this. It just takes a little bit of extra practice compared to the rest of them, okay? Friends, ow, I hit my hand on my table. Friends, thank you so much for joining with me and watching this video with me. I hope it's been helpful. I hope you're feeling a little better about trig equations and identities. And thanks for sharing it with your friends. And thanks for subscribing. I really appreciate it. You got this, guys. Take care.